Okay, welcome back. We're moving on to section 18.4. This is the last section in chapter 18. This deals with spectra. So spectra is a fancy name. I think you probably covered it last semester, but if you haven't, I'm just going to talk about it again. The spectrum of a matrix is the set of eigenvalues. So when we're considering a matrix, the only thing we care about are eigenvalues, and then we combine all of them into a set, and we call that set the spectrum. And of course, this whole section is kind of set up to say, hey, can I play the same game that I play with matrices, but can I do that with these things that I call linear operators, which are kind of like matrices on infinite dimensional spaces, or matrices with functions as inputs or something. And so the question is, can we define a spectrum? Can we define a collection of eigenvalues for a linear operator? Collection of eigenvalues for L, my linear operator, instead of just for a matrix M. And certainly we should be able to do that. Let's just recall what it would mean. Recall that we have an eigenvector, I'll call it psi, if under the map L, the linear operator L, I recover just a number, lambda, times psi, if lambda is just a number, usually complex. So if lambda is any complex number, then we have an eigenvector or an eigenfunction, psi, and we have an eigenvalue, lambda. That's what it means. We want to find those for some arbitrary operators now, in particular differential operators, because we like to use these to solve differential equations. And let's revisit the Schrodinger equation for the particle in the one-dimensional box, where we recover negative h bar squared over 2m d dx squared on psi is equal to some e, which instead of lambda, we're using e here, is equal to a number e, or the energy level times psi. So this was the eigenvalue equation, which basically gave us our solutions to the particle in the box last semester. And in this case, the linear operator, of course, is everything on the left-hand side. So it's h bar squared over 2m, and then two derivatives in x, and then this is your eigenvalue. This is the linear operator. So that is an eigenvalue equation, and by finding the spectrum, in this situation, the spectrum of L was precisely the energy levels which the particle can occupy. This is really interesting because you'll talk about in your physics courses, you would talk about something like, you grab a diffraction grating in front of some molecule that you've excited and heated up, and you're going to recover something that looks like, a collection of lines, discrete lines, and you refer to those as spectra. And in fact, those are precisely spectra. They are these spectra. They are these eigenvalues because those are the energy levels of the electrons in that particular molecule or ion. And those energy levels, when the electrons drop an energy level, they release a photon of a specific energy, and that's why we call this a spectrum here down at the bottom. And actually, it's the reverse of that. So the reason why we call the collection of eigenvalues is a spectrum is because we started kind of with the rainbow spectrum, the diffraction grating, and prisms were splitting white light into its constituent parts, and we already called that a spectrum. But then the physicists and mathematicians were using it so often to describe the spectrum of light, and it exactly corresponded to the eigenvalues that now we use the term to denote the eigenvalues as well. So let's just compute the spectrum of the derivative operator on R, and I'm going to head over to the whiteboard for this. So here at the whiteboard, we're looking for, so to find a spectrum of some operator L, we start with L. I'm going to use y equals lambda y. You could use whatever function you want here. You could use that, but I'm going to use y here. And here we're searching for L equals d dx. So now this is d dxy equals lambda y, and we're going to solve the ODE. Now, it turns out this ODE is a separable type ODE, if you remember from last semester. And the way we solved separable type ODEs last semester was we considered the left as a ratio dy dx equals lambda y. We moved the dx to the left. We moved the dx to the right. We moved the y to the left, and we recover something like dy over y equals lambda dx. And upon integrating both sides, we recover natural log of y is lambda x plus c. And upon exponentiating both sides there, we get y is c e to the lambda x. And so there we have found a eigenvalue, lambda, and eigenvector is the entire thing, c e to the lambda x. So the derivative operator, d dx, has eigenvalue, plural, lambda in R. So any lambda, any number in R, we have an eigenvalue with corresponding eigenvector, which you can also call an eigenfunction, eigenvector e to the lambda x. And you might be a little bit put off by the fact that there's a c in front of that, but just recall, like in the matrix version, mv1 equals lambda v1. If I multiplied both sides of that matrix equation by c and put a c in front of v1, it's still an eigenvalue equation. So eigenvectors are only unique up to a constant multiple. And in fact, the derivative operator has an eigenvalue for every lambda in R. So hence, infinitely many eigenvalues. And this is the first thing that's a little bit different from matrices. Matrices could have at most as many eigenvalues as the dimension of the space that they map, which makes a lot of sense here. We're working in infinite dimensional spaces. We're all of a sudden allowed to have infinitely many eigenvalues. And so instead of only finding finitely many eigenvalues, we will always find infinitely, not always, but in a lot of cases with linear operators, we'll have infinitely many eigenvalues. And so the spectrum of the derivative operator, if I consider the set of all of these, what is the set of every lambda in R? Well, the set of all lambda in R, aka the spectrum of d dx, is precisely R, right? If I consider the set of all elements of R, that's precisely R. So the spectrum of d dx, kind of in the absence of being really, really well formed about the domain of our operator, but the spectrum more or less of d dx is R. So you have absolutely everything in the spectrum of d dx. And the eigenvector or eigenfunction is e to the lambda x, or as they have here, e to the kx. Now, why does this matter? In particular, it matters because if we just modify L and we put an I in front of the derivative, this operator is all of a sudden Hermitian on the closed interval, 0 to L. And from our last section, we noticed that Hermitian operators always have a purely real spectrum, hence purely real spectrum. Of course, back then we just said that it was purely real eigenvector or eigenvalues, but now we can say purely real spectrum and orthonormal basis of eigenvalues, which gives you eigenvectors, which gives you yet one more important thing. Hence, diagonalization. If you remember diagonalization of matrices, it turns out we can diagonalize a differential operator. We can diagonalize something that's infinitely large. And this diagonalization, aka choosing the basis of eigenvectors of this operator, is the next chapter of this book, the Fourier series. So that's where we're headed. Anyway, I'll add another video to this because I know this was a little bit short today, but I'll add another video to this to kind of reinforce what's happening, and then I'll see you in class. Thanks. Bye.